Hello lecturers, and welcome to my presentation on Euler's method. So what is Euler's method? It is a way of estimating the value of a function when we don't have its exact solution. It gives us a close approximation to the actual value based on the slope of the curve at each step. So let's look at the diagram I've drawn here. Suppose we're given a differential equation like dy over dx equals to fxy. This means we know the slope of the curve at any point, but not the actual curve itself. So the red curve here presents the actual solution we're trying to estimate. So we start from a known point, for example, xn and yn, and we look at the blue line, which is the tangent at that point. This tangent is based on the value of fxy, which gives us the slope or the gradient. And since gradient is defined as rise over run, we can take it as yn plus 1 minus yn over xn plus 1 minus xn. And let's say our step size is h. This means that xn plus 1 equals to xn plus h. So substituting that in and rearranging the formula, we shall get Euler's method. So just to reiterate what Euler's method is, yn plus 1 is the predicted value of the next y, yn is the value of y at xn, h is the step size, for example, increments of 0.5 along the x-axis, and fxy is the value of dy over dx at point xy. So let's have an example question of y equals to 2 power x. And we want to approximate its values using Euler's method. So we start at x equals to 0 and y equals to 1. And we choose a step size 0.25. When we apply Euler's method, we will calculate new y values step by step. So here's the table I prepared here. At x equals to 0, the actual y value is 1. So using the method, the approximate value becomes 1.173. So we repeat this process until we reach x equals to 1. Well, estimate of y is 1.915 and the actual y value is 2. So we can see it's quite close of the answer. Now I plotted these results on the graph here. And as you can see that as the step size increase, the estimated graph, the blue graph here starts to drift away from the true curve. So we can conclude that the smaller the step size, the smaller the margin of error and closer the value is to the actual answer. So now let's look at the question we're given. When x equals to 0, y equals to 1. And we're asked to find the approximate value of y when x equals to 1. So I've solved the equation here. And as you can see, I've gotten y equals to square root 2x power 3 over 3 plus 2x plus 1 when y equals to 1 and x equals to 0. And when x equals to 1, y equals to 1.91485 using substituting x equals to 1 into the equation here. And as you can see, the answer is verified when I put it into a graphing calculator and I get the same result. So I tested it with a step size of 0.05 increments of x, and I've gotten the approximate value of y equals to 1.91293,432. And the difference between the actual value is 0.001916. And for the step size of 0.1, I get a value of 1.911375, and the value is 0.003475, which is different from the actual value. So we can conclude that the smaller the step size, the smaller the margin of error and the closer the value is to the actual answer. That is all for my presentation. Thank you.